So a better estimate, I'm going to keep this handy. You guys have this written down somewhere? 12.289 seconds. I want to keep using that value. Okay, thank you. Let's now do the average rate of change from 6 seconds, we'll get to 10, I promise, to the end of the experiment, which was at 12.289 seconds. So that was the first average rate of change. Here's the second one. Now here's where you don't have to panic. Because the average rate of change has always been, and will always be, how much distance over how much time. It's still that. It's still your total distance. I'm going to put total in quotes if that's okay with you guys. Over total time. And the reason I'm putting total in quotes right now is because up top, total distance over total time, total distance was 200 feet. Clearly, it was 200 feet. But that's because I did 200 feet of traveling. But if I'm limiting down my window from 6 seconds to 12.289 seconds, what you're now doing there is the total distance covered is however much distance I covered from 6 seconds to 12.289, and however much time it took me to do that in total. So it's not the total trip distance, it's the total distance between these two time elements, and the total time between those two time elements. One of those is very easy to figure out, isn't it? From 6 seconds to 12.289 seconds is 6.289 seconds, right? You guys buy that? So it's 12.289 minus seconds. Minus 6 seconds. I'll do two fractions, that way we're not assuming anything. Which is 6.289 seconds.
It's 200.
Now the question is now, what goes in the top? Well, we know at 12.289 seconds is 200 feet.
Yeah.
That's 200 feet.
Minus.
We now have to figure out where I was at 6 seconds.
50.
Careful. Oh, this is a great question, but we gotta be careful. Nick says divide 200 in half. 6 is half of 12. What do we assume if we do that?
That you went the same amount of distance.
The trick is that assumes the linear, and I love that you said that. I love that you said that. But the trick with that is that assumes we were traveling linearly the whole time. What that would give you, Nick, is essentially that distance right there. But that's overestimated. 6 seconds, right? 1, 2, 3, 4, 5, 6. It would give us that distance, which is an overestimate. So what I want to know is, think about this. I'm pointing the wrong way. I want to know, Crystal, tell me what's on your mind.
Can't you just go into your table?
You sure can. Now wait a minute. I just got done saying you couldn't use your table before.
But we're going by time this time.
But you have an x value, 6, and you need the y value, time. So you can use your table for this, can't you, friends?
Yep.
You can go right to your table. You can go second y equals. You can go into your table and type in 6 for x, and it will tell you, boom, 50. It's almost a quarter of 200. Isn't that cool, Nick? Not half, not 100, but 50. It would be an overestimate by twice, which actually makes sense quadratically. Thank you for that. It's such a good comment. So 50.234 feet.
So therefore it'd be 1.
So that's only a quarter.
Exactly, versus a half. Isn't that wild? Again, it's quadratic. Quadratic. We're seriously underestimating how fast I was going at the end of this trip. Not that I was going rocket speed, but nonetheless, we can't assume. We need to use the linear model, but way, way closer to what it actually was at the end. Not so. Damn, these fingers apart. Thank you, Crystal, for looking up there and reminding me to do that. Okay, so how much distance is that, friends? 149.766. Notice I'm using a lot of precision. I feel entitled to it a little bit. Because of the calculations. The feet, I'm really not entitled to this much precision in the feet. I'm really not, because of the fact that the feet were measured by my tape measure, which is moving around a little bit. But that's okay, don't sweat that. We're going to get around that momentarily. There's time to get around that deal. What's that come out to be, friends? If you were to divide 149.766 feet by 6.289 seconds, what do you guys end up with?
23.81.
23
feet per second.
Oh, thank you for that. Feet per second. Roughly 50% faster than I was before. Now, what is that?
More accurate.
Well, yes, but Shelley, what's on your mind? What is that? Did you say no, huh? I thought I heard you say something. I could be hearing things. I'm hearing things. It's more accurate, but what is it literally? Not comparing it to something else, but what is that number? 23.81 feet per second. Back over to here. It's the average rate of change between
50 feet and 200
can
feet.
I say 6 seconds and 28, or whatever it was, 6 seconds and 12.289? What it is, friends, different color, let's go green. Yes, who just said that? If I come out to 6 seconds, 1, 2, 3, 4, 5, 6. If I pick a point on the quadratic curve right there, that point is 6, 50. Basically, right? That point right there is 6, 50.234. If I go out to the same endpoint, and I connect those with a straight line, thank you, Britt, that green line has that slope. That green line has that slope. The slope of this green line right here, 23, I keep saying when I say 24, 23.81 feet per second. Why is that more accurate? Good, good. Look at how much different that line is from the parabola. It's not anywhere near as different as the previous line was from the parabola, was it? It's nowhere near as different as the previous line was from the previous line from the parabola was a vast difference. Look at the space. Look at the space between the orange line and the parabolic curve. Much error. As soon as you slide the secant line, this point, closer to this point, you become off less, therefore getting more accurate to the actual true value we're looking for. Now, we're not going to get to this in class. I want to send you guys home with a little quiz to do for Wednesday. But what way can we get even more accurate? Micah?
Narrow the 2 points.
Yeah, leave this point fixed and just keep sliding this point closer and closer and closer. And I'm going to have you do that I made a little quiz for you guys to take with you to practice it between now and Wednesday. But let me show you a TI shortcut first, because this can get a little cumbersome. It's not hard. I'm not saying it's difficult mathematics. It's actually extraordinarily simple mathematics. But you can get these values very quickly using your TI and using some of the built-ins that your TI has. Shelly, I'm going to have to find them on yours, I think. Awesome. Just follow what we're doing. So check this out. We're going to redo both number 1 and number 2 again. We're going to redo both number 1 and number 2. Now, you know what? No, let's just do number 2. Let's not rush it. Let's just get one done. For number 2, we were trying to do the average rate of change between 6 seconds and 12.89 seconds. Now I'm going to swing back to the front for just a moment, because I want you to see something. You know this, but you might not realize this as you're looking at this. These are slopes, right? These are slopes, is all this is.
Yeah.
So somewhere in this calculation is a y2, a y1, an x2, and an x1. And hopefully, it doesn't matter which one you call 1 and which one you call 2. I tend to call 2 the later one. So I would call this y2, and I would call this y1. Is that fair with you guys?
Yep.
And I would call this x2, and I would call this x1. Is that fair? Okay. Now, you could also write it with function notation. Now, I don't know how much of this you guys remember from, okay, Kirsten's saying I don't like that word. That's one of those F words in mathematics, besides the ones I said I'm doing my homework. Function notation is another way of looking at this. Once you have an equation, y equals, whatever we have here, 1.24x squared plus 1.17x minus 1.35. We grow very tired of writing this down all the time. So we store it into our TIs. Conversationally, a way to talk about that would be calling it a function of x, f of x. Do you remember that? F of x, that's all you have to remember. You don't have to do anything with it. Just remember that that's one way to label it. Now that's math. That's math language. Y is a function of X. Your TI uses a different symbol, of course, because they're TI. Instead of calling it f of x, they call it y1 of x. So we stored the function into y1. Please realize, friends, that y1 is not the same y1 as down here. y1 and y2 down here are variable values. That y1 is the y1 that you... Remember how you put y1 after your quad reg? That's the y1 that it's talking about there.
That's the function.
Right. Now here's the beauty. That might seem real...
TI's prerogative.
It's just, well, because we bought their product. It's unfortunate. But here's the beauty of it. Once you make peace with that, watch this. Come on over to here. I'm going to stop and start this one again. Stop.